Hi everyone, my name is Hao. I'm a fourth-year PhD candidate at Harvard studying information theory with applications to privacy and fairness in machine learning. I'm very excited to be here sharing with you a recent project we've done. To split or not to split, the impact of disparate treatment in classification. This is a joint work with Hsiang, Mario, and my advisor Flavio. I'm gonna start with an illustrative example. Assume a data scientist wants to train a classifier for predicting pneumonia. They have samples with features such as chest X-ray. Among all these features, there's a legally protected sensitive attribute, such as race or gender. A natural question is, should the data scientist use the sensitive attribute in the classifier? There are three different strategies for training this classifier. First, the data scientist could disregard the sensitive attribute and use all other features to train a group-blind classifier. When the group-blind classifier is deployed on new fresh sample, it doesn't require the sensitive attribute as an input. The second strategy is to incorporate the sensitive attribute as an input and train a classifier using all the features. This is called a coupled classifier. When a coupled classifier is applied to new fresh sample, it requires not only the features, but also the sensitive attribute as inputs. The last strategy is to split the dataset based on the sensitive attribute and train a separate classifier on each subgroup. We call them split classifiers. In the testing time, split classifiers are deployed on each separate group respectively. To summarize, a group-blind classifier doesn't use a sensitive attribute as an input. A coupled classifier uses a sensitive attribute while sharing other parameters. Split classifiers are a set of classifiers trained and deployed on each separate group. In Drawback et al. 2018, the authors considered how to use a sensitive attribute when it is ethical and legal to do so. They compared the performance of the coupled classifier with split classifiers and showed that using a coupled classifier may lead to an inherent accuracy trade-off between different groups. In this work, we take a step back and consider two fundamental questions. Is it always beneficial to use a sensitive attribute in the prediction task? When does using a sensitive attribute benefit model performance the most? We achieve these goals by comparing the performance between group-blind and split classifiers. This is a non-trivial task. On the one hand, the performance of the classifier relies on the data distribution, and this distribution may vary across different groups. Therefore, using a group-blind classifier may incur an inherent accuracy trade-off between different groups. On the other hand, when sample size is limited, training split classifiers may suffer from overfitting. Hence, there are many factors which will determine the effect of splitting classifiers. For example, the difference of data distributions between groups plays an important role. It is natural to expect that splitting classifiers doesn't bring much benefit if different groups have similar probability distributions. We make this intuition precise and provide conditions under which splitting classifiers doesn't bring much benefit or brings the most benefit. In this paper, we study the fundamental impact of incorporating a sensitive attribute in a classifier. We achieve this goal by comparing group-blind classifier with split classifiers. We study this problem from an information-theoretic perspective. in the sense that we assume the underlying distribution is known, and consider how this probability distribution impacts the effect of splitting classifiers. Before presenting our main results, let me introduce some notations which will be used in this paper. We assume that there is a binary sensitive attribute S, such as race or gender. There are additional features X, such as chest X-ray, which will be used in the prediction task. Furthermore, there is a corresponding binary label, such as presence of pneumonia. Our analysis can be extended to multi-groups and multi-class classification. The unlabeled distribution of features conditioned on the sensitive attribute is denoted by P of X given S. We borrow the terminology from domain adaptation literature and call the conditional distribution of label given features and sensitive attribute as the labeling function. Note that both the unlabeled distribution and labeling functions could be different across different groups. There is a classifier H which will be used to predict the label. We assume the classifier H outputs a predicted probability between 0 and 1. In what follows, we will first introduce an information-theoretic quantity called the benefit of splitting. We provide upper and lower bound of this quantity in order to understand when splitting classifiers benefit model accuracy the most. The benefit of splitting relies on a loss function. By using a different loss function, we can compute the exact values of the benefit of splitting. In order to quantify the classifier's accuracy, we consider the L1 loss. Here, Ys is the labeling function of group S, which the classifier H is trying to approximate. Our analysis can be extended to other types of loss functions, including L2 loss and cross-entropy loss. Now we are ready to introduce the main object of interest, the benefit of splitting. It measures the loss reduction by splitting classifiers compared to using a group-blind classifier. When a data scientist designs a group-blind classifier, they minimize the worst-case loss over all groups. In other words, the best group-blind classifier has loss measured by an inf-max quantity, where the infimum is taken over all group-blind classifiers, and the maximum is over all the subgroups. Similarly, when a data scientist designs split classifiers, they minimize the corresponding loss on each separate group. In this case, we measure the accuracy of the split classifiers by the one which has higher loss. In a nutshell, both the accuracy of group-blind classifier and of split classifiers are measured in terms of the disadvantaged group, which is the group with higher loss. The benefit of splitting introduced in this paper measures the loss reduction by splitting classifiers. This is an information-theoretic quantity, since it depends on the underlying distribution and we don't restrict the search space of the classifiers. In practice, if a data scientist uses a particular classifier, such as logistic regression, then one can define the benefit of splitting by restricting the search space over a hypothesis class. By the minimax inequality, the benefit of splitting is always non-negative. In other words, training a separate classifier on each group will never diminish the accuracy than a group-blind classifier if sufficiently many samples are given. A natural consequent question is, when does splitting classifiers benefit model accuracy the most? We will push this goal by upper and lower bounding the benefit of splitting. The bounds we provide rely on two main factors: the disagreement between labeling functions and the similarity between unlabeled distributions. In particular, the second factor is measured by two different types of divergence. It is worth noting that these factors also appear in domain adaptation literature. Here, we illustrate the factors we have. Each data point has plus or minus representing their label. Two different groups are colored by blue and red. The solid lines are labeling functions with arrow indicating the region where the label is positive. Then we can obtain four different scenarios based on the disagreement between labeling function and the similarity between unlabeled distributions. Here, two groups share similar labeling functions and similar unlabeled distributions. Here, two groups have different labeling functions and different unlabeled distributions. The bounds we have naturally lead to a taxonomy of splitting. Specifically, when two groups have similar labeling functions. By our upper bound, the benefit of splitting is small. This scenario is quite intuitive. Imagine that two groups have the same labeling function. Either a group-blind classifier or split classifiers are trained. The optimal classifier is always the common labeling function. Hence, there's no benefit of splitting classifiers. The second scenario is when two groups have completely different unlabeled distributions, and the benefit of splitting is still small. This is a bit counterintuitive, but imagine that one could design a group-blind classifier, which mimics each group's labeling function on the region where their unlabeled distribution concentrates. This group-blind classifier is feasible, since we don't restrict the search space of the classifiers, and it can achieve perfect accuracy on each group. The last scenario is when two groups have similar unlabeled distributions but different labeling functions. In this case, our lower bound indicates that splitting achieves the most benefit. Also, using a group-blind classifier will always suffer from an inherent accuracy trade-off between different groups. Our analysis can be extended to other loss functions, such as L2 loss and cross-entropy loss. More details can be found at our paper. So far, we use L1 loss for measuring the accuracy of the classifier. At the end of this talk, we will consider a different loss function, and the benefit of splitting under this loss function can be actually computed via an efficient procedure. We consider false error rate as a loss function. It is the maximum between false positive rate and false negative rate. This false error rate plays an important role in fair machine learning literature. For example, equalized odds is satisfied if different groups have the same false positive rate and false negative rate. In this paper, we use false error rate for measuring model performance and plug it into our definition of benefit of splitting. Computing the performance-based benefit of splitting directly is challenging, even with the knowledge of the underlying distributions. This is because the search space of the classifiers is too large, in the sense that any measurable function can be potentially used as group-blind or split classifiers. Solving such optimization problem is intractable in practice. One may attempt to restrict both group-blind and split classifiers over a hypothesis class, and compute the performance-based benefit of splitting empirically in order to circumvent this challenge. However, there are two issues. First, it's unclear which hypothesis class one should pick up. In our paper, we have an example showing that different hypothesis classes lead to completely different approximations of the performance-based benefit of splitting. Second, finding the optimal group line and split classifiers may involve solving non-convex oppositions. In this paper, we provide an efficient procedure for computing the performance-based benefit of splitting. Our procedure converts the intractable oppositions into small-scale convex programs. Here's our main result. The performance-based benefit of splitting can be equivalently written as the difference between two small-scale convex programs, which can be solved efficiently via standard solvers such as stochastic gradient descent. The variables of these two convex programs are mu and nu, which are over two probability simplex. The convex programs also involve a function phi, which depends on a conditional distribution of the sensitive attribute given features and the labeling functions. Here's a proof sketch. Recall that the performance-based benefit of splitting is the difference between an inf max quantity and a max inf quantity. We focus on the first term now. By the definition of false error rate, we can write the maximum as the maximum of false positive rate and false negative rate over two groups. Now we introduce the vector mu, which is in a probability simplex, and the maximum between four numbers can be written as the maximum of a weighted sum. The key step of our proof is to swap the infimum and the maximum by using Gifan's minimax theorem. Then, for a fixed vector mu, we can further simplify the infimum. This expression will eventually become the first convex program in the theorem. We evaluate our procedure on a synthetic dataset. We let the unlabeled distributions of two groups be normal distributions with zero mean and different covariance matrices. Here, ellipses are the level sets of the probability density functions, and the dashed lines are the labeling functions. Theta is a tunable parameter, which is like a rotation angle. When theta is equal to 0, two groups have the same unlabeled distribution and the same labeling function. When theta is equal to pi over 2, two groups have the same unlabeled distribution again, but with completely different labeling functions. In this synthetic example, we can compute the true value of the performance-based benefit of splitting. As shown, when theta is equal to 0, there's no benefit of splitting classifiers. When theta is equal to pi over 2, splitting classifiers brings the most benefit. We also apply our procedure to this synthetic dataset. In this case, our procedure returns the precise values of the performance-based benefit of splitting. Finally, we train optimal group line and split classifiers via SVM, and compute the performance-based benefit of splitting by comparing their false error rate. As shown, computing the performance-based benefit of splitting empirically incurs higher approximation errors and seems hard to interpret. To summarize, in this paper, we study the fundamental impact of including a sensitive attribute in a classifier by comparing the performance of a group-blind classifier with split classifiers. Information-theoretically, splitting follows the do-not-harm principle and benefits the most if two groups have similar unlabeled distributions but different labeling functions. It is very important to note that the decision of whether a machine learning model should use a sensitive attribute is also application dependent and regulated by law. Finally, in the finite sample regime, splitting classifiers is no longer always beneficial. It is natural to expect that more factors will be involved for determining the effect of splitting classifiers. For example, the hypothesis class, the number of samples, the ratio between number of samples from different groups will all play an important role in this case. More details can be found at our paper. Thanks for watching this video.